Okay, hello everyone. It's time to start our today's Astroph. Today we have three presenters, Angel, Dora, and Darian. Uh, who wants to go first?
Okay, I will go first.
Okay.
Start from like Professor Toma. Okay. Uh, okay. So the paper that I want to present today is from Nature Astronomy, titled "Changing Look Active Galactic Nuclei." So the gist here is that AGN typically, we know that their flux varies over time, but that variation is not super, how do I say, not super dramatic. It may be like tens of a percent in variation. But however, with some new observations, we see that these events are a little more common than we had previously thought. With these new observations, we see that these changing look AGN, we see there's actually two types of these events. There are changing obscuration AGN that show that the obscuration levels of the observed AGN changes via column density variations in the AGN. And then there is the second example called changing state AGN, where this time you can think of it as like instead of the geometry of the AGN changing, the actual physics of the AGN varies. Um, and we see, because of this, we see that the broad line emission tend to appear or disappear in different timescales. So basically, we can have type 1 or type 2 AGN. And let me just get into that very briefly. So like I said, we typically observe AGN as changing in their in their flux, but that is not had a big impact until now. So we have the AGN unification model, which for those not familiar with AGN, this basically just says that the AGN that we observe can be divided into AGN type 1, which is AGN that you are looking at from above. You can imagine it. You can see the inner parts of the AGN, allowing you to see the broad line region. And we have type 2 AGN, where you are looking at it face on, it is obscured, and therefore you cannot look at the inside of AGN, or you cannot look at the broad line region that is hidden behind this cloud and the cloudy and dusty tones. So there is the AGN unification model. But over the past 20 years, we have seen increasing number of supermassive black hole undergo much dramatic changes in their spectral properties. And so this goes against this AGN unification model that we see. Um, so yeah, and so let me get into that. So we have changing obscuration AGN, which I briefly introduced earlier, and this is mostly observed in X-ray emission, where the column density increases as a function of time. So sometimes we can see some AGN can be shown to find temporal variations in the line of sight column density. And so they can go from being, they can transition from being obscured by quantum, excuse me, from being obscured by Compton thin material to Compton thick material. And again, this is typically observed in X-ray. And so the most common of these explanations to explain this phenomenon is called eclipses, where basically very briefly, we have clouds going into and out of the line of sight of our AGN. So when we have a dusty, dusty or gassy cloud, come into and out of our line of sight, our column density is going to change. And that is what we see with changing obscuration AGN. So here we can see a brief example of the X-ray spectrum from an unobscured state to an obscured state. And then this is the changing state AGN, which I will explain later. Some other reasons why this could happen, the obscuration could happen, is because of different ionization states of the obscuring gas, but that is not, this explanation doesn't explain most of the events that we see. Some outflows into and out of our line of sight can also change our column density viewing of this AGN. Here we can see some of the obscuration levels. Yeah, I think so. Anyways, then let me introduce, this paper is basically just a summary of a recap of what we know so far about this changing or varying AGN. And so the other type of varying AGN is called changing state AGN, where instead of there are different clouds coming into and out of our line of sight. Here, the actual physics of the AGN is changing. Here we see the broadband region come into our observations, or out and out of our observations, and vice versa. So yeah, so we have the disappearance or reappearance of broad optical UV emissions, and of the accretion powered continuum emission being closely linked. Let me see. And so sorry. Oh. Okay. Yeah. So we know these are changing the actual physics of the AGN, because when we observe it in infrared, there are sort of echoes of these. We can call them infrared echoes. So basically, when the accretion disk gets a jump or a decrease in luminosity, we can see it in X-ray, and then we can confirm it with these infrared echoes that are heating up the gas. So that is what confirms this changing state AGN. Trying to see where it says the rest of this. But anyways, changing state AGN are basically a change in the accretion rates of the AGN, and so that can either inhibit or mitigate the appearance or disappearance of the broadline region in our AGN. That, I think I don't have any more time, but that's about it.
Okay, thank you, Angel. Is there any questions or comments to Angel?
Thank you, Akshan. Of course, this AGN, I have a lot of questions. So, why do you think it's against the AGN unification model, the changing agents?
Because from the AGN unification model, right, it's fully, our observations of our classification of AGN is fully dependent on the angle of how our viewing angle, right? So, but with this, I highlight somewhere, most of the evidence is in the early work section, but basically they state that there have been many examples of AGN transitioning from, for example, type 1.8 or 1.9 to type 1 AGN. So this classification changes in the span of sometimes months, sometimes years. But what your question was why this goes against the well, I think because it is a these variations are as a function of time instead of as a function of viewing angle. I think that's what their
But
point
can't the
was.
viewing angle be changed?
How do you
What
mean?
if what if the galaxy, like the agent, was pointing like this, but not this? Or maybe like the
I don't know how fast galaxies move.
or maybe like the dust which is obscuring has been like, either been
Blown
affected,
away.
yeah.
Yeah. I'm not sure.
How do you differentiate basically between these two phenomena?
Which two phenomenon?
Like if it's an evolutionary thing or if it's a unification.
I would say, well, if we're talking about like AGN or galaxy evolution, in my head that takes like millions of years. Or that's like a very long time range. But here they're mentioning the time scales of months or years.
Right.
So that's what I interpret. That's what I get from this. So that is why they say this is strange. This goes against the unification. I don't know if that's the answer you were looking for.
So maybe I would suggest that there are some videos by Vicky about this paper,
Okay.
and has given some talks in ESO. So maybe you should check them out.
I was looking this guy up recently. Yeah.
So if you check his videos, he has a lot of work done regarding the changing location, especially in this regard. So maybe just have a look at it because he explains why this obscuration, the changing look is against the unification.
Oh.
And, also, I think now it's more important because we have this data, right? We have this data with various intervals.
Mhm.
So that's why it's possible that we can do this changing we cannot. If we only have one epoch data, then it's not. Yeah. So yeah.
Thank you.
Okay, thank you, Priyanka and Angel. Is there any other questions or comments to Angel? If no, we can move on to Darian.
Mhm. Today, I want to present this paper. This brief paper called Eternity 6 Hours Intergalactic Spreading of Intelligent Life and Sharpening the Fermi Paradox. I don't know, maybe some of you here is already know what is the Fermi Paradox is, but I will start from the same questions. So the Fermi Paradox is we know that our universe has a lot of uh, there are a lot of systems like stars can be colonized by some intelligence outside our intelligence, I mean the aliens. But until now, why we cannot see the aliens? So in this paper, they also mention, put more simply, why we cannot see the aliens that should be out of there. And this paper tried to uh, discuss about how the Fermi paradox can be extended or maybe to explain more. And they use methods using common knowledge in physics. So they want to know how, so for example, the aliens exist and how they can colonize from one galaxy to another galaxy systems or something. So the first thing they start from this expanding the paradox. So the contributions of this paper is to sharpen the Fermi paradox by demonstrating that intergalactic colonization is feasible task for a civilization capable of interstellar colonization. So then they start to mention about the exploratory engineering. So the exploratory engineering is the art of figuring what techniques are compatible with known physics and could be plausibly reached by in the future human scientists. So maybe they use a common physics, but maybe this physics, even this physics is common for us, but it doesn't mean that in engineering level they can create by today, but maybe for future civilizations they can do. So the arguments is here. So to colonize from one galaxy to another galaxy or from one stars to another stars, the alien should create a self-replicators or probes. So here they also mentioned that maybe this means that we to make a self-replicators, the alien should use the AI, like Betty mentioned. Betty always mentioned about AI, so maybe Betty is interested in this. So AI as a technology that may be plausible for humans or aliens over the few next millennia, they can use this technology to detect. So in figure one, this is the symbolic representations of exploratory engineering. So the axis here means that the technology that we know today. So the exploratory engineering is beyond the engineering what we know today. And this is forbidden because there is a limitation, right? So even you have a very advanced technology, there is a limit. So this is forbidden because of the laws of nature. And they discuss about the probe and replicator design. So the replicators here, they okay, the replicator or self-copying paste is a system to drive a payload from one system to another system, something like that. So if you want to colonize another stars, it means that you have to move some equipment from the first colonized stars to uncolonized stars. So you have to bring your equipment there. So they also discuss the data storage that alien may need. So they say that they can use a diamond constructed by the carbon 12 and carbon 13 as a bits here. So they can use a diamond to do a computation. And they also can, make a size upper limits. It's from the project called Daedalus project, similar as a human did before in 1980. So I'm also curious that like this is claimed that NASA's self-replicating lunar factory design. I think NASA is also love aliens, but they try to not admit. And then the upper limits is 500 tons in weight. And then the lower limits is in the scale of 10 to minus 18 kilograms. This is called the Merkel-Freitas HC molecular assemblers. But we currently have no engineering pathways that would lead to such of that tiny assemblers because of the laws of quantum physics also prohibits you can get more smaller and smaller. So to building an example in nature, they need to use this kind of data. And then the second aspect is the deceleration. Why deceleration it's also considered here? Because if you send the replicators from one places to another places, and you don't have any deceleration machine, so you may hit a new system and you cannot replicate by yourself. So you need to decelerate your probe or something to another system. So they mentioned that they can use a magnetic sails. They use the magnetic energy to slow down the system. And to design the rockets, they can employ the relativistic rocket equations. It means this is the fuel needed to do relativistic speed here. And they can use the nuclear fission standard reactions and also nuclear fusion too. So as you see here, so so they so they mention here in table 3. So this is the matter and antimatter combinations or fusion in kilograms, the fuel they need to achieve the 50% of the C, 80% of C, and 99% of C. This is the speed you can achieve by burning the fusion or fission process. And they also counted the collisions, interstellar dust, and redundancy, because when you send the probes, the collisions may happen. So they say the set of the critical impact energy that could be happened by the collisions or something. It's about here. So this is the critical density is 10 to minus 35 gram per centimeter cube. And then what? So they also discuss about the launch phase. So the launch phase is to colonize another stars is using the design of the Dyson sphere. They try to create the Dyson sphere. So before creating Dyson sphere, they should disassembling the parts from their probes to create a Dyson sphere. So it takes a lot of energy too, because they have to, encounter the gravity of the system. So if in the Mercury, for example, is about 1.8, 10 to 30 joules, is a huge energy to do that. And then to launch the probe, they also discuss about the launch system. So the power you need to disassembly the Dyson sphere is higher and higher from years to years. And then the mass remaining during the assembly of the Dyson sphere is lower and lower because it's disassembled, but it takes a long time to do that. So they also discuss that, because the universe is also expanding, so the galaxies distances, the moving distances may be, like farther to each other. So they employ the Friedman equation in here. So how to tackle this expansion, so you need, like boost or something to achieve the same, the same time. So, but according to this kind of scenario, so why until now we cannot see them, right? If known physics is available for them, they are so intelligent, but why? So this is arguments that may use. So here, if the expansion is feasible, so I make it shorter. So the civilization is universally, maybe they choose not to expand because we are so dumb. Maybe they say it's a cultural filter because we are not too good. So and then, or maybe this is the catastrophic events prevent expansion. It's called the great filter. This is what I do in my paper. So I introduce the astrophysical hazards there. Maybe they trust them before we see them. So, and the third one, we are among the very first. So, I mean, this is the rare earth hypothesis. So, I think this is, this analysis to, in short, this analysis to that, aliens may know our physics, and then the aliens can do this kind of physics, but they do not invade us because these three, you know, reasons maybe. So that's what this paper want to say, roughly.
Mhm. Okay, thank you, Darian. Is there any questions or comments to Darian? If no, we can move on to Dora.
Okay, today I'm going to talk about searching for gamma ray bursts associated with Chi FRB. So, because FRB and gamma ray bursts are both linked to compact object activity, so they are trying to find a connection between FRB and gamma ray bursts. And in this paper, they use the FRB data from Chi and the gamma ray burst data from Swift. And as we know, the event rate of FRB is 1,000 times per day. And also for gamma ray bursts, they separated gamma ray bursts into two kind of, one is short gamma ray burst and the other one is long gamma ray burst. And the short one means the duration time is smaller than 2 seconds, and the long gamma ray burst, the duration time is bigger than 2 seconds. So first is for FRB sample. They use Chi catalog too. So there's 4,500 FRBs in total, and there's about 981 birds from 83 repeater. And so there's 3,500 are not repeater. And also China only provide the localization uncertainties. They also provide the localization probability maps for each FRB. So they use 4,513 FRB events, which have reliable localization maps. And for gamma ray burst sample, they use there is 464 events from Swift. So there's their workflow of the association procedure. So they input the FRBs and gamma ray burst sample. So the first thing they will consider the localization based matching, and they will consider the redshift, and then is the temporal consistency. So first is the localization based matching. So the localization maps encode the full positional probability distribution on the sky, so which is non-Gaussian and irregular due to the instrument being response from Chi. And they evaluate the confidence level and at the gamma ray burst sky position by interpolating the FRB localization map to check if the gamma ray burst position lies within 68% region. So after the localization based matching, there's 113 FRB, 130 pairs for FRB and gamma ray burst. And they consider the redshift consistency. So they infer FRB's redshift from the observed dispersion measure. And for gamma ray bursts redshift, they use from a multi relation. then is the temporal consistency. Because the long gamma ray bursts are commonly associated with massive star collapse. So that means it will give rise to a long-lived compact object. So FRB activity will be after the gamma ray burst. So it will delay. And for short gamma ray burst is linked to compact binary mergers. So FRB expected to occur contemporaneously or after any pre-merger radioactivity. That is because the long gamma ray bursts and short gamma ray bursts have different progenitor. So it makes the temporal consistencies different. Okay, so in the beginning, we have 4,513 FRBs and 464 gamma ray burst events. So after localization batch matching, there's only 130 pairs. And also after the temporal ordering, there's 80 pairs with FRB time minus gamma ray burst time equivalent to it, means that the FRB happens after gamma ray burst. And also after the redshift consistency, there's only 45 pairs. And there's only 28 pairs for these for this. So, and I also excluded 2 short gamma ray bursts in this 28 pairs. So there is 26 pairs left. And I also run this is the sky distribution for the FRB and gamma ray bursts. The gray dot is for China FRBs, and the blue one is the gamma ray burst, and the yellow one is for the candidate pairs. And I also run the simulation. The gray region is the simulation result, and the red line is for real match sources. And the p-value is, if p-value is large, that means the coincidence are random. But for these two, these two, when p-value is small, that means random will not produce that much coincidence. So these two probability indicate that these deviations are not statistically significant. And they also shows 4 pairs. In this paper, they mentioned that for 2 top panels, these 2 pairs are coincidence. Because we can see the green, the gamma ray burst is within 0.68 confidence level. But for the top panel, the gamma ray burst is in the side lobe. That means it's still close to the FRB center, but it is not observed by main beam. And the bottom 2 panel mentioned the gamma ray burst is offset, but for these 4 figure, they said that, but after I see into these 2 images, I think maybe these 2, the second one and fourth one are coincidence, and the first one and third one is offset in my eye, I think. So let's go to the conclusion. In this paper, they adopt full localization probability maps instead of simplify error ellipse from localization uncertainty. And they also consider the physically motivated temporal criteria. And they also run MCMC, so they have 26 pairs, but random simulation will produce similar number and distribution like the like paper's way. So, but the small contribution from genuine association cannot be excluded because of the high localization uncertainty, small amounts of sample, and sky coverage. So the real event will be diluted. So they need more sample for this job. This is my presentation. Is there any question?
Identify the redshift and so the redshift will be very important.
Yes. You mean for redshift?
Okay. How they check the redshift consistency?
For here, because FRB is according to Macquarie relation. So if the DM value is from China catalog, so we have Macquarie relation, so we can infer the Z value for FRB. But for gamma ray burst, they use this equation to know the redshift. It is a multi-relation, but I not really know.
Both these relations give the redshift with large uncertainty.
Yes.
So how do they check the redshift consistency? Because it's like if the error is 0.5, then is it over? May not.
I think maybe they use likelihood. Is that true? I'm not really sure. Thank you.
Okay, thank you. Thank you, Dora. Is there any other questions or comments to Dora? Okay, if not, um, is there any volunteer for tomorrow? You? Mutu? Mohan? And one more person? Is there any other volunteers? Okay, thank you, Tomaki. If there is no other specific questions or comments, we can close the meeting now. Thank you so much for attending. Thank you. See you tomorrow.